So we're going to relate or relating quadratic forms. And the three forms we're going to talk about are the standard, sorry, I don't know why that slipped my mind there. Standard form, the factored form, and the vertex form. Okay. I'll write the original ideas there. Y is equal to a x squared plus b at x plus c. I'll write those letters in. The letters here are kind of important because there is a bit of a relationship between them. Each of them represents something different graphically or a different relationship. The factor form is y. Actually, I should apologize. In our case, we've been using f at x, so we're going to use function notation instead. So we'll say f at x. And this function is equal to f at x is equal to a again. And that does represent the exact same value, so do keep that in mind. X minus r, x minus s are the two terms they usually use. So r and s. And then finally, vertex form. I don't want blue. F at x is equal to, and you'll notice a is there once again, and that term is constant throughout all three of the versions. X minus h plus the letter k. So other than a here, a that happens to occur in all three of the forms, which means if this is the number one, it's the number one no matter how we rewrite a quadratic equation. The other letters, B and C, R and S, and H and K, they are independent. They are strictly related to the form they're in. You only see a B representation of a number and a C representation in standard form. R and S only in factor form, and H and K only in vertex form. So they don't pertain to any of the numbers in the other ones. What we've done beforehand here is going to jump across. We have three different forms, and what I'm going to do is I'm going to make some notes. So we'll kind of do this. Here's standard form. Do you know which of these three, the purple, red, or black one, is the standard form of the quadratic equation? Do you know off the top of your head?
The red?
Yeah, the red one's the standard form. So we'll use that to help us organize. And then we have factored. Do you know which one is the factored form?
Black.
Yep. And then by default, that means the other one must be the vertex form. Okay. I'm going to spell it right. We're going to rewrite them on the other page, and then we're going to talk about how we can find different pieces of graphical information from each of them. So 2, -16, and 24 is the standard form. So this quadratic in standard form is written as f at x is equal to 2x squared minus 16x plus 24, I believe it said. Okay. In factored form, it was f at x was equal to 2, x minus 2, and x minus 6. And in vertex form, it was written as f is equal to 2 again, x, I want to say 4, minus 8. I think that's right. Let's jump back across. Yep. Great. Oh, what a memory. Okay, so the reason, we should put this out here, the reason they use a is because technically this isn't the quadratic, this is a quadratic. This is one of the infinite types of quadratics that we can build, okay? So that's why we use this function using variables, is because we could substitute all kinds of different numbers into there. It just so happens right now we've written this one, and the factor form of this quadratic is written like this, and the vertex form of this quadratic is written like this. And we can prove this on the graphing calculator by kind of turning off the colors of the other one. We'll notice it's red. And then I turn this one on, the black one perfectly overlaps it, which means, yeah, this is the exact same. And when I turn on the purple, it's a little hard to see with the black, but the purple overlaps the black one too. Okay, so what that means is these are the exact same quadratic, just represented in a different way. Now what we want to do is draw attention to parts of the numbers in the quadratic and what they can tell us about them. So for instance, in standard, graphically, only the C really gives us any information. And the C happens to be the y-intercept, okay? So in this case, 24 should be our y-intercept. And if we do a little zooming out and move around the page, you'll notice that at 0 and 24 is our y-intercept. So since that is the standard form, I'm going to add an extra line just below it because that's what standard form gives us. We'll put an expression. I'm going to put it just before. We'll put the coordinate of 0, 24, label it as the y-intercept. It's nice, but intercept. There we go. Okay. So we have the y-intercept there. We know it's at 0 and 24. So that's all that standard form really gives us about a graphical representation. Okay. Factored tells us what our roots are. So in this case, roots are x-intercepts. These two values in here, assuming the a value is 1, tell you the root. If the a value is not 1, then it's a little more complex and you have to set the parenthesis or the bracket equal to 0 and then solve for x. But if we're written in a form where a is equal to 1, then we can kind of find the opposite. Really what you're doing here is you're saying 0 is equal to this bracket, and I'll work it out really quickly. Oh, that's funny there. X minus 2. And the reason it becomes opposite is because when you isolate for x, you bring it to the other side, well, you use the opposite operation. So that's why we think of it as using the opposite, okay? Same idea here. 0 is equal to x minus 6. We move it to the other side, it becomes positive 6. So the root or x-intercept is positive 6 and positive 2. If there was an a value here, we would have had to do a little extra division to isolate for x. So that's really the process. But they show you with simple forms of quadratics. In factor form, when they're simple, in other words, the a value in front of x is just 1, then you can find this really, really quickly. So with that being said, let's double check if that's correct. Let's add in another expression. In fact, we're going to add in 2 expressions because we get 2 coordinates from it. We knew one of the coordinates was at -2 and 0. Okay. Oh, I lied. Sorry. That was what it was written when it was factored. Here's x-intercept. So there's one of them. And the other one should be 6 and 0. Label intercept. Okay, so we've got the 2 x-intercepts. That's what the factor form gives us. And again, so I wrote in -2, but remember we had to isolate that bracket by setting it equal to 0, and when we did that, it became positive. So that's why I have those positive x-intercepts. Finally, the vertex form is pretty straightforward. It tells you exactly what it's going to give you. It tells you what the vertex is going to be. And in this case, that happens to be the h and the k value. The h value is the x value of the vertex. So if we were to write it as a coordinate, okay, because there are 2 coordinates to the vertex. So this would be the h value. And the k value is the y value of the vertex. So in this value, we do k, h. And in this case, I'm going to write just below it, we end up with a coordinate that says, so remember that this is very similar to the scenario with our factored. Because it is x minus h, the x value of the vertex is actually the opposite of this operation. Because when we plugged it in, it would have said x minus +4. So we had 2 operators beside each other. So we simplified them by just writing a negative. Had this been a positive, that means we would have originally had a negative value for the x. So in this case, it's +4. And the k value is what you see is what you get. It's -8. So we go back over to our graphical representation. We find out, hey, what is this? -4, comma, sorry, not -4, right? It was +4. +4 and -8. We get a label. And that is our vertex in this case. Perfect. So those 3 forms give us different pieces of information about quadratics. Each of them give us an important piece. And really, once you have the x-intercepts, y-intercept, and the vertex, you can do a rough sketch of a quadratic. Once you can put these 4 coordinates, and x-intercepts don't always exist. Sometimes you can only get a y-intercept and a vertex. And then Sometimes the y-intercept is the vertex, so you really only get the vertex as a major coordinate. This can give you a general idea of how to sketch it. I will bring to your attention the other thing. If you remember back to like your intermediate science, the idea of changing between a solid and a liquid and a gas is we can interchange between these three versions pretty freely. What we do is they don't all have an official name, but when you go from standard to factored form, you actually go through the process of factoring. Okay, so that's what we kind of talked about some factoring before. And if you go from factored to standard form, you're actually going through expanding or distributing. We're just going to put the word expanding for now. Okay, usually they call it expanding and simplifying or distributing. From standard to vertex, there's a couple ways to do it. The common way, it's taught is called completing the square, which is probably what you'll get into. But there are a couple formulas you could use, just like there's actually a quadratic formula you could use to take standard to factored. I didn't actually talk about that, but that is another way. Completing the square is a common way to do it. If you're going to go back from vertex to standard, you actually use the same process from factored to standard. It's the same as vertex to standard. You expand and simplify again. Okay, so always going back to standard from these two, we're always expanding. It's a little trickier when going between factored and vertex. You can always, just like driving on a map, you can always go to a point of reference you're familiar with and then drive here. But if you want to take the shortest distance, to go from factored to vertex, the idea would be to you find the axis of symmetry. I'm going to call it the AOS in this case. Find the axis of symmetry and then substitute. I'm just going to say sub. You substitute the y value in, and that might not mean much to you now, but once you start realizing what these processes are, you'll hopefully make a little more sense. And when you go to vertex form, what you can do is you set it equal to 0. So we'll say set equals 0 and isolate x. Again, not really a formal name. At least I don't know. There may be a formal name for it. But these are the processes of going between them. So just think about like if you're going from a liquid to a gas to a solid, you had sublimation, evaporation, condensation. Same idea. We just use different processes here. Okay.